Levent Hoca hazır. Tamam. Kullanmak isteyenlere açıyorum. İşte şu slide bizim de bir program. Ben burada durayım. Ben birazdan gelirim hocam.
Tamam. Şimdi hoca şey yapacağım.
Sunumunu bir başlatan falan gidelim.
Tamamdır. Sağ olasın.
Bir giriş yapıyorum. Bir şeyi vereyim.
Evet. Buyurun. Buyurun. Güzel. Sayın
Ses geliyor mu?
ekranda ben görünmüyorum. Geri. Şimdi oldu. Evet. Hocam sizin kadar tecrübeli değiliz. Okay. Sayın hocalarım, öğleden sonra oturumuna hoş geldiniz. Today we have 5 more presentations, and then we have an invited guest here, Associate Professor Dr. Serkan Ünal. He is giving us a presentation on sustainability for polymeric fibers and textiles. Okay, yes. Serkan Hoca is from Sabancı University. He received his bachelor degree from chemistry from Koç University in year 2001 and completed PhD in organic polymer chemistry at Virginia Technical University. And I think he worked as a research scientist at Bayern Material Science in Pittsburgh. And he joined to the Sabancı University in year 2012. Hocam buyurunuz.
Hocam 60 benim sınavım. Yok. Ömer görebiliyor musun?
Hocam olmadı. Yine PowerPoint sayfası ya.
Ömer.
Sesim geliyor mu?
Okay.
Hocam duyabiliyor musun?
Normalde olması lazım. Ben bitirdim.
Okay. Hi, everyone. I would like to thank the organizers for this kind invitation. And I'm not coming from far, so I'm from Sabancı University. And today, I'm going to talk to you about our recent research on recycling polymeric fibers from textile products. And I'm a chemist, by the way. I'm not a textile engineer, but hopefully I will try to make the connection between the two disciplines. So if we have a look at the outline of the talk today, I'm going to talk about plastics in general, plastic manufacturing, production, how the waste is currently being managed globally, and what can be done within the circular economy of plastics. And then I'll touch on textiles, because textile waste is, somewhat correlated with the plastic waste management, especially for the ones that contain some polymeric raw materials. And then next, we are going to touch on the existing recycling technologies for plastic waste with a short comparison of these existing technologies. And then I'll touch on the solvent-based recycling that we have been working on for the last 4 years at Sabancı University, which is related with the project called ISOPREP, funded by the European Commission on recycling of waste carpet, which is, which can be seen as a textile product. And then, remaining part of my talk, I'll be talking about what we have done in the project so far, and then finish up with conclusions and acknowledgements. This slide is, I think it's quite basic, but, plastics are everywhere in our life. I think it's quite well understood now. We are sitting on plastics, we are using plastics every day. Sometimes we are throwing them away after a single use. Sometimes they are with us forever. But overall, the use of plastics is rapidly increasing in our life. And then it brings a lot of things. It enhances the quality of our life. It makes our lives easier. And then, of course, on the other hand, there's always a I don't know why this is changing by itself, but hopefully I'll keep the pace. There's always a problem with the plastic waste. And then maybe until today, it wasn't a huge problem, but nowadays with all the plastic pollution affecting the environment, there's a huge debate going on how to handle plastic waste. And if you look at the numbers, there's a huge increase in the global plastic production worldwide, as you can see the numbers actually, and some estimates, as you can see from, especially starting from 2010, it's estimated to be rapidly increasing. And, this is fine, and it makes sense because we are becoming more mobile. We are moving around a lot compared to previous years. And when we use lightweight materials, durable materials, and all these can be done with plastics. However, if we look at some numbers in terms of how we handle the total amount of plastics we have manufactured globally, so we are talking about since 1950, we are talking about 8,000 million tons of plastics produced globally. And then, a good portion of it is still in use. And, majority of this plastic we have generated globally has been disposed of. And if you look at the actual numbers in the way we dispose these of, a very small portion, about 10% of the disposed plastic is recycled. And the remaining part is mostly incinerated and or goes to landfill, which is a huge problem these days. And then if you look at the ratios now, the landfill is about 80% of the plastic waste, and about 12% goes to incineration and 10% goes to recycling. However, as you might be closely following from the existing calls from the European Commission and all the agents funding research projects, the circular economy in the plastic recycling has to be followed. First of all, the overall goal is to be able to create a circular economy to reduce need for fossil fuels, petroleum-based products, to minimize waste, to reduce the environmental footprint, which is quite critical, and to generate income from the plastic waste. From this perspective, I think plastics are one of the most promising types of materials because, although we have been so far designing very complex plastic products, especially food packaging materials, some textile products, etc. Overall, there's a good control over the structure of plastics, and if you design them properly, you can probably make them more recyclable. Textiles, on the other hand, are quite interesting, very functional materials as well. Apart from clothing, they are used in a variety of applications such as medical, construction, agriculture, and etc. Of course, the environmental impact of the textile industry is quite critical, because we all know during every phase of textile production, there is a waste generated. Sometimes wastewater, sometimes some polluting chemicals. But at the end of the use, of course, there's a textile waste as well. And then, this waste is generated when the product becomes unusable. And then, apart from that, we can generate waste during any stage of the textile manufacturing, during spinning, weaving, knitting, dyeing, finishing, and under use. Even during washing and drying, we generate waste, which is also unfortunate. And then another thing is, of course, we are buying more clothing every day. Compared to 15 years ago, people are buying 6% more clothing. And then, just in the United Kingdom, people buy 2 tons of clothing every minute, which is quite higher than the rest of Europe. And then globally, every year, 56 million tons of clothing are bought every year. And this is expected to increase to almost 100 million tons by 2030 and 160 by 2050. And of course, this will have a reflection on the waste people generate. And right now in the United States, each consumer is generating roughly about 37 kilograms of textile every year. And then globally, it's about 92 million tons of textile waste generated every year. And then textile industry is, is using about 10% of the raw materials around us. And then this 10% is directly reflected on the greenhouse gas emissions for the whole industry, all industries globally, and it's about 10% as well. And then if you look at the current picture, this is a very nice picture actually. The current picture is not very nice. Right now, for the textile industry, 97% of the raw materials are virgin feedstock. Only about 1% is coming from a circular economy type principle or closed loop, and 2% from other industries. And then as we generate the textile product, we have about 10% loss during production, some waste generation during use in the form of microfibers, which also needs to be addressed. And then after use, about 73% is landfilled or incinerated, but some, I think 12% is recycled. And this is not a good picture, of course, from the circular economy principle. And people have to start looking for ways to increase the recycling rate, not just the recycling rate, the closed loop or circular economy type of recycling. And if we look at some other products, paper, for example, 66% is being recycled right now. Glass, 27%. PET, which is commonly used by the textile industry, 29% is recycled, and this is mainly from bottles, not textiles, of course. And therefore, if you follow the directives and regulations from the European Union, you can see terms like design for sustainability or design for recycling, which is quite critical. People nowadays choose monomaterial type applications or designs so that it can be recycled. Also, another thing people do is use sustainable materials, which is derived from renewable resources, not necessarily fossil fuels. And of course, at the end of the day, recycling is quite critical. And if we look at the textile recycling market in the United States, which can be thought of 1/3 of the whole world, you can see that it's increasing, and it's a very decent market actually, which is about almost $5 billion. And if you look at it, you know, majority is of course cotton-based systems, polyester, there's wool, polyamide, and some others. And you know, as a polymer chemist, we are heavily interested in the polymeric materials used in textiles in terms of recycling. And one of those materials is polypropylene, which can be very commonly found in waste carpet. In fact, waste carpet is a very significant contributor to the polypropylene waste. And actually, polypropylene carpet itself is holding about little less than 20% of the whole polypropylene use. And almost half of the carpet market is based on polypropylene market. And then in the UK alone, in the United Kingdom, each year they generate about 400,000 tons of waste carpet. And majority of this, 66%, goes to landfill. So, you know, with all these facts, an effective recycling system for this complex waste had to be developed. And then once this recycling system is developed, another main goal would be to reduce the need for polypropylene from fossil fuels. Aside from carpet waste, polypropylene is the second most used commodity polymer, so you will see them everywhere. And the global polypropylene market has been rapidly increasing, and the majority of the waste polypropylene actually goes to landfill. With all these facts, you know, I think the critical thing or the critical question is how can we recycle them? If you look at the existing recycling technologies for plastic waste, people can do a variety of different things. Of course, the easiest route would be to reuse it if possible, but of course not always possible. Another easier method would be mechanical recycling. So without doing any complex chemical or without any complex process, you can basically reprocess the product and obtain a recycled product. And then another approach, which requires a bit more energy compared to the mechanical recycling, is a solvent-based recycling, or sometimes it's called solvent-based purification, which allows you to obtain a product in the form of pure polymer or pure plastic. Of course, in some cases, in the case of, for example, especially polyethylene terephthalate, you can see some cases where you see depolymerization. You go back all the way to the building blocks, which is then repolymerized to obtain a product. And then there are some more complex technologies such as pyrolysis or gasification, which will take you all the way to the refining raw materials. If we look at this chart from the energy requirement point of view, if you go from right to left, you need more energy to do all this. And then if you go from left to right, you would end up with decreased quality of the recycled product. Here are a few examples of inputs you currently used in different types of recycling processes, such as mechanical recycling, PET, polyolefins, polystyrene, PVC, some mixed plastic. They are heavily used. You can use solvent-based purification or polymer-based recycling for a variety of polymers. Depolymerization is very common in PET, which is, I think, very well established. And I think today one of our students has a presentation on this. And then pyrolysis and gasification is always interesting for the big industrial companies because they already have existing investments on hydrocrackers, and they want to be able to feed raw materials into these existing investments, and both of them allow them to do so. But of course, they also require a lot of energy. This is a comparison of all the existing technologies from their advantages and disadvantages point of view. As I tried to explain, mechanical recycling is easier, okay? but of course, it doesn't give you the ultimate product always, and it's not a solution to solve the plastic waste problem by itself. Solvent-based purification, which is, the topic of today's presentation, I think it has a very special position in between mechanical recycling and depolymerization. First of all, it retains the polymer structure. It gives you a low carbon footprint. Even at small scale, it can be profitable, and it's suitable for multi-layered or multi-component waste mixtures, which is also important because most of the problematic plastic waste around us is multi-component, so people cannot separate them really unless they depolymerize them one by one, or use techniques like pyrolysis or gasification, which is quite more difficult and energy intensive. Of course, it has some limitations, which we also try to overcome. Most of the time it's limited to single stream polymers, so your solvent-based system would be, used for single stream, although we have also proven some ways to separate different polymers from each other. Some additives may come all the way with you to the end of the process. And then, when you use higher temperatures and etc., you may end up with having some minimum degradation on the polymer structure. Depolymerization, it's self-explanatory, but the problem with depolymerization is you need repolymerization, which is also energy intensive. I won't touch on the pyrolysis and gasification, but they are also great, interesting topics, especially for petroleum industries like SABIC and ExxonMobil and other big chemical companies. To summarize solvent-based recycling, it's been around actually for a long time, since 1970s, solvent-based recycling, or as a polymer chemist, we always do purifications using solvents, so it's not a new thing. But of course, you have to come up with a process that enables the selective dissolution or extraction of the specific polymer out of a mixture, purification of it, and then recovery of it in the form of high purity. But here are the steps for that. You first need to dissolve the polymer in the selected solvent. You have to apply a series of filtration to remove any undissolved materials. You need to do a precipitation in a non-solvent, and then do a few steps of washing and drying. Okay? And then at the end of this precipitation, you can easily separate the two solvents. Your solvent used for polymer dissolution and your non-solvent for precipitation, you can separate them by distillation. But again, as I tried to imply, it has a few different advantages. You can remove additives or impurities using this technique, and you can precipitate your polymer after purification in different forms for further processing, including fiber formation. And then at the end of the day, you can obtain raw materials as good as a virgin grade polymeric raw material, okay, which can be used in any kind of application. Of course, repolymerization step is eliminated in solvent-based recycling, and then you can apply it to a variety of different waste mixtures. This timer says I have 10 minutes, so I will try to summarize what we have been doing within our project called ISOPREP in the last 4 years. So ISOPREP was proposed 4 years ago to the European Commission to propose to come up with an innovative alternative approach for the recycling of end-of-life polypropylene product. And then within this project, we chose carpet waste as a good model. For this purpose, we developed a ionic liquid-based solvent which can selectively dissolve polypropylene out of the multi-component mixture, and then we aim to obtain a virgin quality polypropylene, which is price competitive at the end of the day. And then at the end of the project, nowadays, our pilot system will be up and operating within a few weeks here in Turkey, actually. The project is a consortium with 10 partners across 5 countries, coordinated by the TWI, the Welding Institute in the United Kingdom. And from Turkey, we have Sabancı University as well as Flotex, a plastics company in Bursa. We have Fraunhofer University of Graz, Senti, London South Bank University, and some machining and waste handling companies. So, at the end of the day, as we said, our main goal was to obtain high purity grade plastic raw material out of this carpet waste mountain. So the first thing we did was, of course, we had great textile engineers in our team, but we wanted to understand the composition of different types of waste carpet that we had from our partners. And we screened almost 30 different waste carpets. And then if you look at this chart, we had different compositions. Some of them had a very high level of polypropylene content, which was desirable, but some of them did not. And first thing we had to do was we had to separate these before going into the solvent-based recycling. And then we went in and we did a very diligent study to investigate all types of components in this waste carpet. And as you can see here, very different materials from polyethylene to polyurethane, SBR, and etc. were found in the same carpet as a backing material. And then at the end of the day, as summarized here, we found more than 10 different components in these waste carpets, which makes our lives more difficult, of course. And then as we aim to selectively dissolve polypropylene in this waste, we first had to understand the effect of these other components in the carpet. So we did a leaching study at various temperatures. Through a systematic study, we investigated the leaching behavior of each component in our solvent. We looked at the color change, we looked at the weight loss, and then from here, we were quite fortunate that only 2 of the components, polyurethane and SBR, which are both in the form of foam, backing material, were a bit problematic in terms of their behavior in our solvent. So what we did is we looked at the weight change, and of course, we basically, based on this study, we needed a pre-process that can enable us to obtain higher polypropylene content in our waste and remove these undesired components. Since they were in the form of foam, once you bring them down to a smaller size, it was easy to get rid of them by density differences and etc. And then here are 2 pieces of data. This is a thermometric analysis before the pre-process waste carpet as this. As you can see, this weight loss is due to the polymeric component, which is polypropylene. And then as we pre-processed it, we increased the polypropylene content dramatically. We also looked at the melting behavior of the polypropylene content in the mixture. As you can see, we also increased it from about 63% to 75% based on the DSC. So what was next? Basically, next we had to do the dissolution, and we had to do all these in a lab scale setup looking like this. Okay? So this is a very neat and innovative setup which can do all sorts of solvent-based recyclings and then precipitation as well. First, we looked at the dissolution behavior of our waste in our solvent, and at different concentrations and different temperatures, we looked at how rapidly we can dissolve it. And within an hour timeline, we were able to dissolve almost all of our material in our solvent. And then once we did the recycling, we characterized the recovered polypropylene in terms of the carbon and nitrogen content. So this is pure polypropylene with very low levels of nitrogen, about 86% carbon. This is the pre-processed carpet waste with 70% carbon and slightly higher nitrogen content, but once recycled, we were very close to the carbon content that was seen in pure polypropylene. We did some structural characterizations such as FDR and NMR, which all verified the purity and the structure of polypropylene we obtained. And if you look at the thermodynamic behavior of polypropylene, we obtained in red versus pure polypropylene, you can see identical behaviors. Similarly, in DSC, they showed very similar melting behaviors. So once we obtained these results, our next step was to scale up this process in our own laboratories at Sabancı University. So working with a great team, we were able to design a system like this on our own, where we could do all the dissolutions, filtrations, and precipitations together in a system operating at the university laboratory. I hope these work, but here you can see the dissolution process, okay? So it's intensive and it's hot inside. And here, if you look carefully, you can see pure polypropylene dripping into our non-solvent. Here, right here. Of course, it's a polypropylene solution in our ionic liquid. And then this is the mixture of our precipitated polypropylene in the ionic liquid and the non-solvent. So in conclusions, we developed, we believe we developed a novel methodology to obtain high purity polypropylene from a multi-component, very complex waste carpet. We confirmed the high purity by its properties compared to pure polypropylene from fossil fuels. We also demonstrated that the new process has no effect on the chemical structure of polypropylene. We were able to remove all the solvent in the recovered polypropylene. We checked all the thermal transitions and etc. And we were able to recover 90% of polypropylene present in the waste carpet using this method. And then our partners in Portugal, actually, they were able to spin this polypropylene yarn out of 100% recycled polypropylene we produced, which is a very rare example of a study, because if you look at recycling studies, they mostly use a little bit of recycled polymer and most of the virgin polymer. But in this case, this is a 900% recycled polypropylene yarn. And then this is the overall process overview of isoprep, in which we can come up with a circular economy principle from waste carpet to neat to a high purity grade raw material back to the yarn and back to carpet. So what's going on around us? Actually, this technology is not something, or I would say that we are not the only crazy ones trying to do something like this. Actually, there is a technology we are following closely in the United States called PureCycle. Feel free to go and look into them, but they are using a more complex process to purify polypropylene out of different waste. And they have a 7 tons per year pilot system up and running, and they have a 50 kilotons per year industrial scale facility just opening this year. So, and they have significant investments in the future from Japan and from Korea. So this type of recycling is in the agenda, and you will see more of these in the upcoming years. With this, we would like to acknowledge the European Commission Horizon 2020 program, which funded our project. Great colleagues from all of our partners around the world, from the UK, from Germany, Austria, and Portugal, as well as Turkey, Voltex. And of course, our team. We had really great people. Serkan Güçlü from Istanbul Technical University Environmental Engineering program. Nuray Kızıldağ, who came to us as a textile engineer and material scientist, and who is now a great scientist in polymer recycling. Professor Menceloğlu, Professor Dizman, they have supported us greatly, and our technician Erdal, who has done all the work in the lab by himself. With this, I would like to thank you for your attention. I hope it was somewhat interesting for you, and I'll be happy to have any questions you have.
Gramming of polypropylene, recycled, when you compare, what are the properties are same? How much they can
It depends on a few things. If you compare the 100% version of the virgin grade of the recycled versus the virgin grade, you will see very small differences. But we know the industry, including the pure cycle, they do a few steps of compounding, and they bring their virgin polypropylene to the same position as virgin PP. So the answer is, with a few percent additives, they will be exactly similar.
I just wanted to learn how environmentally friendly is yours.
That's a great point. Of course, being environmentally friendly changes, or the requirements change every day nowadays. First of all, energy is one critical thing. And then, of course, the solvent. We are using a solvent at the end of the day. And in this project, we have a goal to retain 99% of the solvent throughout a year in the process. Right.
Recycle the solvent.
Right, exactly. We reuse the solvent again and again.
And you
Are
don't
we there?
release it to the
No,
nature.
we cannot do that. Our system is closed anyway, so we cannot let it evaporate. Are we there yet? We have some calculations to do to verify this, which is done by our partner at Fraunhofer Institute. But looking at that lab scale pilot system, we are not using the solvent. So it's a closed system. We do a distillation separated to solvent. But another point is the energy use. And if you compare the production of virgin grade polypropylene from petroleum resource versus a process like this, we are talking about the use of 70% less energy compared between the two. 70% less energy, 40% less carbon footprint, and those two make a huge difference. Actually, those are the numbers which allow pure cycle like companies to get investment for a phase process like this.
Because the idea behind recycling is actually to be environmental friendly.
Right.
So, and also the other reason is to use not the fossil sources for energy. Therefore, to produce polymers.
Right.
When I hear that I use the solvent and the solvent system, not so friendly environment.
If you can use the solvent again and again, there is nothing wrong with it. As most of the environmental friendly polymers right now, for example, paint, okay, the majority of them are produced with the aid of a solvent in the factory. Yes, we get it waterborne, but they use solvent to produce those polymers, but they use the solvent again and again. If you don't use the solvent, if you don't let it evaporate, or if you don't emit to the environment, there's no problem. We will be using these chemicals no matter what.
No, just to picture all these things, if everybody uses the solvent to solve the polymer to reduce, to reuse again, and we have the companies all over the world. They sold the polyethylene and they sold the polypropylene. There they sold. I think then in total you don't have a very environment again.
It all depends on calculations. I tried to see your point, but if you look at the existing petroleum-based polypropylene manufacturing, it's a very, very energy intensive, high carbon footprint system. Plus, we are trying to recover already manufactured polypropylene. So this has no carbon footprint compared to the one that's produced from virgin.
Çok geçtik sana. Thank you for your nice presentation. So this is a small gift from us. And
Thank you.
okay. Now we have our second presentation. Nasıl geriye döneceğiz? Okay. Now our second presenter is Gamze Sakallı. Her topic is Türkçeymiş bu. Çevre dostu polyester ipliklerin kıvrım davranışının konvansiyonel polyester ipliklerde karşılaştırılması. Gamze Hanım Uludağ Üniversitesi Mühendislik Fakültesi Tekstil Mühendisliği bölümü mezunuymuş. Şu anda Ustaoğlu Tekstil Ar-Ge merkezinde Ar-Ge uzmanı olarak görev yapıyormuş. Buyurun Gamze Hanım.
Herkese merhabalar. Ben Gamze Sakallı Özbal. Tekstil yüksek mühendisiyim. Tekstil yüksek mühendisiyim. Şu anda Ustaoğlu Tekstil'de Ar-Ge uzmanı olarak çalışıyorum.
Gamze Hanım 15 dakikada bitirebilirsek.
Tamam. Tamam hocam.
Ömer Hocam görebiliyor musun?
Gayet iyi hocam. Hocam duyabiliyor musunuz? Sıkıntı var ya.
Tekrar merhaba herkese. Ben Gamze Sakallı Özbal. Tekstil yüksek mühendisiyim. Ustaoğlu Tekstil Ar-Ge merkezinde Ar-Ge uzmanı olarak görev yapıyorum. Bugün Aslı hocamızla birlikte çalıştığımız çevre dostu polyester ipliklerin kıvrım davranışının konvansiyonel polyester ipliklerle karşılaştırılması konusunu anlatacağım sizlere. Tekstil ürünleri temel özelliklerini kumaş yapısını oluşturmak için kullanılan ipliklerden alıyorlar. Tabii ki birçok farklı iplik kullanarak biz kumaş yapısı oluşturabiliyoruz. Ama sentetik iplikler için konuşacak olursak ham madde ve kimyasal yapısı ve üretim metodu ile biz ipliğe farklı özellikler kazandırıyoruz.
Ondan gidememiş, kusura bakma.
Estağfurullah.
Bir ismini.
Kaldığım yerden devam ediyorum. Sentetik iplikler için konuşacak olursak ham madde ve kimyasal yapısı ve iplik üretim metodunu değiştirerek biz farklı özellikler kazandırıyoruz ipliklere. Böylece son ürünün kullanım alanına göre iplik seçerek kumaş üretimi gerçekleştiriyoruz. Özet olarak iplik bünyesinde barındırdığı tüm özellikleri nihai ürününe yansıtıyor. Sentetik iplik grubuna bakıldığı zaman en çok polyester ailesine mensup olan ipliklerin kullanıldığını görüyoruz. Tekstil hazır giyim ve deri ürünleri 2021 sektör raporuna göre dünya genelinde 2018'de 100 milyon tonluk elyafın 55 milyonu polyesterden oluşurken geri dönüştürülmüş polyesterlerin payı 20-30 bin tonla kalıyor. Firmalar 2025 ve 2030 hedeflerinde aslında bu rakamı yükseltmeye çalışsalar da şu anda konvansiyonel polyesterle yarışabilecek bir durumda değil hala henüz. Bunun genel olarak sebeplerine baktığımız zaman tekstil sektörü üreticileri açısından özellikle baktığımız zaman çevre dostu, sürdürülebilir recycle ürünlerin konvansiyonel muadillerine kıyasla istenen performansı göstermemesi ve maliyet açısından bu ürünlerin daha yüksek olmasıyla alakalı olduğunu görüyoruz. Bizim bugün paylaşacağımız kısım aslında çok daha geniş bir çalışma bu. Biz kıvrım özelliklerini paylaşmak istedik sizinle. Kullanım alanına göre tabii ki değişiyor ama kıvrım, elastikiyet, geri toparlanma ve hacim özellikleri iplik için istenilen özellikler arasında ve tekstilde çok kullanılıyor. Genel olarak çalışma kapsamında kıvrım, elastikiyet, geri toparlanma ve hacim özellikleri iyileştirilmiş 10 adet çevre dostu kompozit iplik tasarımı gerçekleştirdik. Bu ipliklerin iplik numara tayini yapıldı ve kıvrım özelliklerinin karşılaştırılabilmesi için dokuma kumaşlar elde ettik. Sonuçlar yüzde kıvrım cinsinden karşılaştırılarak değerlendirildi. Literatürde hem çevre dostu ürünlerle alakalı hem kıvrım özellikleriyle alakalı hem de bizim birazdan bahsedeceğim materyallerimizle alakalı birçok literatür çalışması var elbette. Ama bizim onlardan farkımız ve amacımız direkt olarak aslında şu, tekstil sektöründe sık kullanılan polyester grubuna ait iplikleri kıvrım, elastikiyet, geri toparlanma ve hacim özelliklerini bilinen yöntemlerin dışında iyileştirmek, çevre dostu sürdürülebilir ipliklerle kompozit iplik oluşturarak fonksiyonel özelliği arttırılmış iplik elde ederken aynı zamanda da çevre dostu sürdürülebilir yeşil ürünlerin maliyet faktörü de göz önüne alınarak ön plana çıkmasını ve kullanım alanının genişletilmesini sağlamak. Materyal olarak 4 tane materyal kullandık. Hepsi tekstüre iplik ve genel olarak denyeleri 150 denye. Zaten bildiğimiz klasik polietilen teraftalat var. İkinci ipliğimiz bir komponent polietilen teraftalat, polimetilen teraftalat. Burada ikinci ipliğimize, bir komponent ipliğimize özellikle dikkat çekmek istiyorum. Burada PTT bildiğimiz üzere mısır nişastası gibi yenilebilir kaynaklardan elde ediliyor ve yarı alifatik bir polyester. Glikol kısmında 3 metilen birimi bulunuyor ve yapısında zikzak moleküler yapısı olduğu için bu iyi esneklik, üstün elastik kazanım ve yüksek hacim yumuşak tuşa kazandırıyor. Diğer ipliğimiz recycle polyester ve burada kullandığımız diğer dikkat çekmek istediğim sonuncu ipliğimiz biodegradable. Bizim orada biopet olarak nitelendirdiğimiz, kısalttığımız biodegradable polietilen teraftalat. Bu çalışmada kullandığımız biopet ASTM D5511 standardına göre analiz edildiğinde ipliklerin aerobik olarak, biyolojik olarak parçalanabilir olduğu görüldü. Normalde 300 yıllık bir polyesterin doğada parçalanma ömrü var. Bu iplikler 3 ila 5 yıllık bir süre içinde parçalanıyorlar. Belirlenen materyalleri ikili kombinasyonlar olacak şekilde iplik üretimi gerçekleştirdik. Yöntem olarak katlama ve büküm yöntemi tercih ettik. İplik katlama makinesine kaplanan iplikleri 436 tur bölü metre S yönünde büküm uyguladık. Ardından da iplik bükümünün kalıcılığını sağlamak amacıyla 100 santigrat derecede 60 dakika boyunca fikse işlemi gerçekleştirdik. Bunlar elde ettiğimiz kompozit ipliklerin konfigürasyonları. Bunlar da mikroskop görüntülerimiz. Kompozit ipliklerin yüzde kıvrım ölçümlerini değerlendirebilmek için dokuma kumaş üretimi yaptık. Çözgü sıklığı 20 tel, 300 denye 192 filaman polyester efektli iplik kullanıldı. Atkı sıklığı da 15 tel olacak şekilde uygulandı. Kumaş, tamam hemen hızlanıyorum hocam. Kumaşlara son olarak 15 metre bölü dakika hızındaki ramöz makinesinde işlem uyguladık. Deneysel sonuçlara geldiğimiz zaman şöyle ilk önce iplik numara tayini gerçekleştirdik. İplik numara tayini gerçekleştirdikten sonra herhangi bir anormal durum gözlemedik. İplik kıvrım testlerini de şöyle kıvrım tespit cihazında gerçekleştirdik. Bizim burada kullandığımız aslında kompozit iplik olarak ürettiğimiz iplikler atkı yönünde kullanıldığı için sadece atkı yönündeki yüzde kıvrım sonuçlarını paylaştık sizinle. Burada da kıvrım sonuçlarını görüyoruz. Kıvrım sonuçlarına baktığımız zaman yüzde 3.40 ile en yüksek kıvrımı bikopet kombinasyonuna sahip kompozit iplik gösteriyor. Bu durum aslında az önce bahsettiğimiz bir komponent iplikte kullanılan PTT lifinin özelliğinden de kaynaklı bir sonuç. En düşük kıvrımı da 1.74 ile PET Recycle PET kompozisyonuna sahip bir iplik gösteriyor. Zaten 1.74'ten sonra peşinden onu takip eden %1.76 ile PET kompozisyonuna sahip iplik. Sonuç olarak genel olarak değerlendirdiğimiz zaman çalışmayı, çevre dostu sürdürülebilir ürünler farklı üretim yöntemleriyle kullanıldığında hem istenilen özellikleri sağlayabiliyor hem de fonksiyonel özelliği artırmış ürünler elde edebiliyoruz. Hem de dünyamız için etik değerlerden çok artık zorunluluk haline almış bir sorun olan doğal kaynakların tüketilmesi ve çevre kirliliğinin azaltılması yönünde katkı sağlanabileceğini öngördük. Kaynaklarımız. Dinlediğiniz için teşekkür ederim. Buyurun hocam.
Toplumlar arasındaki fark ne kadar? Bunların bilgilerini paylaştık. Bunlar aralarında istatistik olarak fark var mı? Bazen bu rakamların artı etkileri olduğu için birbirinden mesela birinci ile ikinci arasında bir fark yok diyebiliriz. Bunlar hangisi birbirinden farklı?
Standart sapma değerleriyle aslında hocam haklısınız, onların sonuçlarını vermem gerekiyor. 5 hocam. 5 tane farklı. Evet. Evet. Evet.
Teşekkür ederiz Gamze Hanım.
Ben teşekkür ederim. Sağ olun.
Şunu takdim edeyim size. Teşekkür ederiz.
Ben teşekkür ederim hocam. Sağ olun.
Buyurun. Bir sonraki sunumumuz Yunsa Ar-Ge Merkezi'nden yün iplik üretim hattı teleflerinin geri dönüştürülmüş iplik ve kumaş geliştirilmesi. Duygu Hanım Yunsa Ar-Ge Merkezi'nin yöneticisi. Kendisi 9 Eylül Üniversitesi, doğru hatırlıyorum değil mi Gamze Hanım? 9 Eylül Üniversitesi mezunu, doktorasını da yaptı ve şimdi inşallah doçentliğe hazırlanıyor Gamze Hanım. Sanayiden dersler veriyor. Ondan sonra dışarıdan inşallah sanayiden ilk doçenti de göreceğiz inşallah. Değil mi Gamze Hanım? Lütfen buyurunuz.
Sunum ekranını değiştirmek için ellemek istemedim bunda olduğu için ama.
Şöyle. Şuradan mı geliyorduk? Şu mu?
Evet.
Tamam. Şöyle tüm ekran yapalım.
Evet. Tamam. Öncelikle tamamdır hızlıca. Öncelikle merhabalar. Hepiniz hoş geldiniz. Ben Yunsa Ar-Ge Merkezi'nden. İsmim Duygu Yavuz Kasap Ayak'ta. Yün iplik üretim hattı teleflerinin özellikle bizim fabrika bünyemizde çıkan üretim hattındaki elyaf iplik ve kumaşların atıklarıyla ilgili neler yapabiliriz diye mercek altına aldığımız bu projede Şule hocamız ve Demet hocamızla birlikte çalıştık. Benim sunumum özellikle Yunsa Ar-Ge Merkezi'nden biraz kısaca bahsetmek ve giriş, özet, amaçlar, materyal, yöntemden sonra deneysel sonuçlar ve genel sonuçlar olarak paylaşımları sizinle paylaşmak. Kısaca şöyle bir görselimiz var burada. Nerede anlayacağım ama ses vardı, gelmiyor. Öyle değil. Yunsa Ar-Ge Merkezi olarak 2010 yılında kurulduk biz. Şirketimiz 1973 yılında kurulmuş. Avrupa'nın lideri ve dünyada ilk 5 kumaş, yünlü dokuma kumaş üretici grubundadır. Kamgarn iplik üretim hattı ve Şitrergan iplik üretim hatlarına sahibiz. Kamgarn dokuma kumaş üretimi olarak yıllık 10 milyon metre kapasiteye sahibiz. Ham maddemiz elyaf, açılmış elyaf ya da elyaf tops formunda gelerek Kamgarn ve Şitrergan hattındaki üretim proseslerine göre süreçleri ilerlemektedir. Bunun dışında ham maddemiz geldikten sonra iplik formlarında dokuma boya işlemleri ve apre işlemleri de kendi bünyemizde gerçekleşmektedir. Nihai ürün olarak da kumaş olarak sevkiyatları yapılmaktadır. Yunus Ar-Ge Merkezi'nde özellikle Wool Road diye bir marka tescilini aldığımız dergimiz var. 2019 yılında gazete olarak çıkarmaya başlamıştık ama 8. sayı itibariyle Mayıs ve Ağustos aylarında da en son çıkardığımız sayı 8. sayı itibariyle de marka tescilini alarak paydaşlarımızla da paylaşmaya başladık bunları. Çok yakın dönemde de tekstil mühendisliği bölüm başkanlarımıza ve başkan yardımcılarımıza da gönderdik. Daha da kapsamlarını genişleterek biraz daha farklı içeriklerini zenginleştirmek istiyoruz. Ar-Ge merkezimizde 30'dan fazla TÜBİTAK projesi tamamlamış durumdayız. 2 tane Avrupa Birliği projemiz var. Şu anda Temmuz itibariyle de 5 patent, 5 faydalı model tescilimiz bulunmakta. 60'tan fazla da yayına imza atmış durumdayız. Gün özellikle en akıllı olan doğal lifin lüks grubunda yer aldığı için bu ham maddelerin atıklarının bir şekilde daha katma değerli ürünlere dönüştürülebilir mi diye açıkçası ilk etapta bu sorgulamayı yaptık. Çekme makinelerinde, penyöz makinelerinde ve fitil oluşum aşamalarındaki elyaf atıklarının toparlanarak tekrar recycle edilmesiyle ilgili bir organizasyondu. Elde edilen kumaşların performans özellikleri değerlendirilerek ticari değeri olan katma değeri yüksek bir ürün elde edilmiştir. Bu kapsamda gerçekleştirilen kumaş da ceketlik bir kumaş ve satışı da gerçekleşmiştir. Giriş kısmında biraz literatür vardı. Burayı hızlıca geçeyim dilerseniz süre açısından. Literatürde baktığımızda yünün özellikle karbon salınımının yüksek olduğu ve küresel ısınma potansiyelinin en yüksek olduğu lif olduğunu görüyoruz. Özellikle üretim sürecindeki metan gazı salınımıyla birlikte çok daha fazla recycle edilmesinin anlamlı ve önemli olduğunu özellikle çalışmalarda görebiliyoruz. Bizim iplik ve kumaş üretim aşamalarında çıkan atıklarımızı öncelikle sınıflandırdık ve bunları mercek altına aldık. Bugün sizlerle paylaşacağımız olan kısım elyaf atıklarla ilgili olan kısım. Şıttergan iplik üretim hattında harmanallaçtan belli proseslerden geçirerek en son bobin aşamasında materyal elde ediliyor. Bu aşamalarda özellikle çekme makinesindeki ve renk makinelerindeki ve fitil haline getirildikten sonraki aşamalardaki elyaf teleflerinin toparlanarak değerlendirilmesi sağlanmıştır. Atık elyaf teleflerinin fotoğrafları görmüş olduğunuz gibi P1 ve P2 olmak üzere verilmiştir. Bu kapsamda elyafların, öncelikle toparlanan elyafların incelik değerlerine, lif boyu uzunluklarına bakılmıştır. Bant ölçüm kısımlarından nepste ve çöp tayini gibi klasik olan elyaf analizleri yapılmıştır. Ardından iplik özellikleri için iplik numara, büküm, mukavemet gibi, düzgünsüzlük ve tüylülük gibi ses cihazlarında
Paylaşım bilmiyormuş da.
Bu kapsamda biraz önce görmüş olduğumuz P1 ve P2 olarak elyaf atıklarını çözgü ve atkı ipliği olarak %25 ve %35 oranında sağmal dediğimiz ilk ham maddenin içerisine ilave ederek iplik tasarımları gerçekleştirdik. Bu kapsamda çözgü ipliği olarak ve atkı ipliği olarak farklı harmanlardaki iplikleri oluşturduk. Konstrüksiyon bilgisi de yine görmüş olduğunuz gibi normal genişen tezgahta işte belli tarak numarası ve uygun iplik numaralarında 14'e 1 olarak iplik çekimleri sağlanmıştır. Bunu ilerletemiyorum ama bu sefer de. Mukavemette düşüş olmadı. Önce elyafların özelliklerine bakarak değerlendirdik. Elyafların incelikleri de ince iplik grubuna denk geldi. Onların özelliklerini de birazdan paylaşıyor olacağım. Baktık. Sonrasındaki kumaş değerleri de çok uygun çıktı. Kumaş test sonuçlarını da paylaşıyor olacağım şimdi. Materyallerimizi özellikle kendi ürün gamımızda bulunan kumaşlara yaptığımız testleri yaptık. Bunlar klasik mekanik testler, uygun standartlarda ve uygun test cihazlarında Günsa bünyesinde. P1 numaralı biraz önce göstermiş olduğum P1 numaralı elyaf grubu için elyaf analizlerinde yapılan testlerde çıkan sonuçlar mikronlarına bakıldı. Uygunluk olarak NEPS sayılarına, çöplerine ve uzunluk olarak da uygunluğuna bakıldı. 60-64 milimetre ve uygun 18 ila 19 gibi uygun mikronlarda gözlendi. Akabinde oluşturulan 14'e bir enem olarak hedeflenen iplikler için çözgü ve ipliklerinin test sonuçlarına bakıldı. Normal işte numara, büküm, uster, ince kalın hepsinde mukavemet uzama değerlerine bakıldı. Bu kapsamda çözgü iplikleri oluşturulan ipliklerin dokuma performansı için yeterli mukavemette olduğu görüldü ve kumaş oluşumu gerçekleşti. Oluşan kumaşın yani apre aşamaları da gerçekleşti. Bu arada biz armürlü dokuma tezgahları kullanıyoruz. Dornier sert kancalı 350 devir bölü dakikada kenarları lene olacak şekilde 15 santinewton uygun formda bir kumaş yapısı geliştirildi. Bu kapsamda kumaşların testleri yapıldı ve gayet uygun kopa mukavemetleri, yırtılma mukavemetleri ve martingale test sonuçlarına bakıldığında gayet anlamlı ve ideal test sonuçları elde edildi. Tuş açısından da uygunluk olarak okeylendi. Koleksiyonumuza koyuldu ve satışı gerçekleşti kumaşın.
Eski hızlarda değişiklik oluyor mu?
Neydi?
Eski hızında version
Yok, olmuyor.
aynı hızlarda
Evet, aynı hızlarda çalışabiliyoruz. Yok, gözükmüyor. Kullanılan kaynaklar özellikle onbaşıydı. Beni dinlediğiniz için çok teşekkür ederim. Sorularınız
Evet. Eksik yapılan projenin karşılığını bulması. Soru var mıdır? Arada hocam sordu. Hocam teşekkür ediyoruz.
Ben teşekkür ederim.
Şu
Çok
bugünün
sağ olun.
hatırası
Çok
için.
teşekkürler.
Şurada katılım belgemiz var mı, resim çeken? Nerededir? Yok. Peki
Şey,
efendim.
şey
Miray
çekiyorum.
çekiyor bana. Ben de neye bakıyorum.
Tamam. Evet. Çok teşekkür
ederiz.
ederim. Sağ olun.
Bir sonraki sunumumuz Our next presenter is Dr. Mansur Bidoki from Yazd University. His presentation topic is development of a water recovery and recycling system for the airjet texturing process. Yes.
Sunum gözüküyor mu? Korkmayın. Son ekran değil mi? Şu an yok.
Good evening, everyone. It's a real pleasure for me being here and talk about wastewater recycling in different areas of textile industry. I'm so honored to be a part of group led by Professor Demir at ITU, and fortunately, we are going to start a Center of Excellence for Wastewater Recycling for textile industry with the help of all of you, and it will be our main pleasure to have you and your cooperation in that center. It will be announced later on, and it will be a real nice opportunity for all of us to take part in this important issue. If you know, I'm from Yazd University. Yazd is in the center of Iran, in a deserted area. Our ancestors learned how to bring water and how to care about it. We don't have water resources over there, so we bring waters from 100 of kilometers out from mountains to the city through canals or some underground tunnels. It was, for example, 500 years ago, they did it. So in that case, we are now bringing water from the sea to our city to use it for the industrial applications. And because I was from the textile industry, we started something to recycle back whatever is inside the wastewater to the actual production plant. One of the possibilities is returning back the water from an oil-containing wastewater, which is from air-jet texturing process that I'm going to discuss it now. But my main message here is to think about wastewater recycling as serious as you can. It is possible, the technology is there, not 100%, but at least, you know, the technology is ready for implementation. We shouldn't be scared of that, and we need to take action for recycling back water from the wastewater, not to pollute the environment, and on top of that, not to use the water resources. So as you know, textile industry is the most water-consuming industry in the world. And when textile industry is using water, causing water scarcity, and on the other hand, it produces lots of environmental pollution. So we need to think about it very wisely. Is there enough water for us to use from these resources? Definitely, you know, the statistics shows that there is not enough water for using in the industrial application, and day by day it's getting more restricted and not available. So they like to use water for feeding human animals, producing foods, rather than using it for the industrial purposes. For example, each tons of textiles usually consumes 100 tons of water in the production, from cultivation up to the end of the process. And usually all the waters or most of the waters turns to wastewater, polluted wastewater. And what is the normal practice? They are treating it and discharge it to the environment as a not completely clean water. Some kind of cleanliness it does have, but not completely. So what we should do, this is one issue. We use water from underground or rivers, and after that produce wastewater, then treat it and discharge it to the environment. So in that case, the water is going to be scarce, and we don't have enough water sources. But at the end of the day, there is a limitation, and we have to recycle wastewater back to the factories. And this is the only solution. We have to think about it. And the recycled water should be reused in the application. And hopefully, with starting this Center of Excellence for Textile Wastewater Recycling and Reuse for a sustainable future, we all together can make a change in the Turkish industry, in the Turkish textile industry, And if we save even 1 liter of water, it's worth thinking and talking about it. Usually wastewater from textile industry does have lots of impurities, like dissolved substance, dyes, biologically degradable, non-degradable materials, and one of them is oils and fats. And because the paper is about the air texturing system, usually during the air texturing system, the yarn, which is a multi-filament yarn, would be pushed by compressed air to have its different structure, to some extent closer to natural fibers. And in that case, they have to make the yarn a bit wet. And this wetting happens before the contact of the compressed air with the fiber. In this area, when you make the yarn wet, the water can wash out some spin finish oil from the fiber, and that spin finish containing water would come out as wastewater. And what's inside the spin finish, more than 50% of that is oil. So oil containing water would be waste and discharged to the environment. So can we use this oil containing water? We say yes, we can. Why? Because oil usually does have a different density from water. It can freely float on top of water, but if it is emulsified, it's been mixed with water. And what is the obvious sign of being emulsion? Making water milky. Why it's milky? Because the oil particles are separated in water, and when the particle size are close to the wavelength of visible light, the particles can change the direction of light when it passes through, the same as fog. Usually the light should pass through air, but when there are tiny droplets of water, the light cannot pass directly due to the Mie scattering, and something like this happens. So look, instead of going straight forward, it goes to the other directions. And this scattering depends on the diameter of the particles, and on the other hand, the difference between refractive index of the particles and the matrix, which is air. Or for example, in the fibers, we do have the same thing. We are using titanium dioxide as a opacifying agent, and the refractive index of TiO2 is, for example, 2.2 when polyester is 1.7. So delta N makes the fiber opaque. So when the oil is mixed with water and it is emulsified, it's going to be milky. The same mechanism makes cloud opaque. So we have to remove those kind of oils. And what kind of system we've got in hand to treat the wastewater? There are many: biological, electrochemical, advanced oxidation, microbial, photocatalytic process, and membrane separation. But all of them does have some limitations. Not all of them are working perfectly. But if they work, the water should be cleaned from the oil and then can be used for irrigation or discharging to the environment. But we are thinking about recycling back to the factory from this route. So whatever we do, we remove the oil and bring it back to the factory for reuse. What are the normal practices for removing oil? If the oil is free on top of the water, rope mops, skimmers is the best solution. There are ropes can absorb oil and bring it out, and then squeeze. The oil comes out of the rope, and again, the process will be cycled. The other process is DAF, or dissolved air flotation. So air would be dissolved in high temperature in water. Then it removes air from the water, making bubbles, and the bubbles brings oil on top of the water and will be removed by some paddles. Some electrocoagulation techniques works well, or organic clays can be used. But all of them does have some limitation and problems. We have started thinking about finding the best solution, which is easy to handle for everybody. And it can work with different concentrations of oil. And this is the company we have started to work on that. And the same technology was used for this, to do the experiment of this paper. So because of the time, I'm skipping something. So this is the wastewater received from an air texturing company. Just by simple chemical process and just with a simple mixing process, it can be like this. It is possible, everybody knows that there are something which can work like this, but the sludge should be easily separated, should not be sticky, and should be easily compressed to be able to remove from the water. So the wastewater could be clear like this, but as you see, electrical conductivity would be a bit higher because there are some chemicals added. pH can be controlled, suspended solids are lower, COD are lower, but not in the range of discharging to the environment, but it's enough for using it in the process. And oil content is still not zero, but it's much lower than the original oil content. And with a simple process, something like this, you can mix the first chemical that produced from that company, then the second chemical, and easily the sludge is removed. The sludge would pump to a filter pressed and goes out as a chemical waste, and the clear water goes to the factory and can be used again and again. And in this case, the waste recycled water should be without any smell, without any bacteria, that with chemicals you can handle it. And the process should be low cost and low space requirements. And if it works automatically, so it's much better. And the sludge can be pressed just by a simple filter press or any other kind of screw press, belt press, even centrifugal press. So different kind of assemblies can be installed in the factories, and it can recycle back oil-containing water very easily, much better than maybe some electrocoagulation processes, which are very hard to control. They are very good, but hard to control. But this process is very easy to handle. If factories start using this technique or any other technique, I don't care about the technique they are using. The main thing is that recycling back the water. They save money for purchasing less fresh water by tanker, because if the water is coming from the well, it's very cheap. But if it's from the tanker, it's going to be more expensive, and definitely by recycling, they are saving some money. Worry-free production, because there will be no environmental restriction and stoppage on their operations. Receiving 50 to 100% of electricity charges back as a bonus from the government. Attracting more European and American customers who care for the environment, the most like Zara, Marks & Spencer, and other big brands, because they are forcing their supplier to there's no use for another RO system or resin softening, and saving water resources, and at the same time saving the environment for the next generation. And this is my main message. Wastewater recycling and reuse is not only a system to purchase, it's a culture to follow. So whatever you do, and the hardship of that is this one. You cannot push a button and just look at it and it works. No, you should take care of that. It can work automatically, but if you care about it, if you want to use it, definitely it works. And I hope that every one of you start thinking seriously about wastewater recycling and reuse. Thank you so much for your time, and I'm ready for the question. Thank you so much.
For this last presentation.
Yeah.
I have one.
Yes, please.
We recycle the water and reuse it in the industry.
Yes.
But you mentioned about the oil residue inside it. Is there a possibility to reuse it and discriminate the particles from it? Or what is your plan to reuse it?
As for example, for air texturing process, you only need to remove the spin finish from the fiber. And as long as the oil content of the water is reduced, so there is a capacity for this water to remove a spin finish. Maybe there is a need for 10% increase in the flow of water, but definitely it can remove the oil. And again, you remove, for example, 90% of the oil, and the cycle can last forever.
This is a small gift.
Thank you so much.
Thank you so much. Thank you. Thank you for the presentation. Okay, our last presentation. Okay, our last presentation is again from Sabancı University. The topic is investigation on the efficiency of the catalyst system and use in the chemical recycling of polyester. Serhat Köre is from Sabancı University. 2021 yılında Sabancı Üniversitesi Malzeme Bilimi ve Nanomühendislik bölümünden mezun olmuş. Kimya bölümünde yandan yapmış ve şu anda Sabancı Üniversitesi Malzeme Bilimi ve Nanomühendislik bölümünde yüksek lisans eğitimine devam ediyor. Buyurun Serhat. 15 dakika kuralım uyarsak sevinirim.
Zoom'a geldi mi?
Hello, I am Sarah. I am a material science and nanoengineering student in Sabancı University. And today I'm going to present my study, which is called as an investigation on the efficiency of the catalyst systems used in the chemical recycling of PET. So first of all, I will talk about what is PET, why we need to recycle, PET recycling methods, aim of our study, methodology, results, conclusion, and the future works. So first of all, what is PET? PET is a thermoplastic polymer, and it is very convenient for the production of beverage bottles because of its high strength, low weight, optical transparency, and low CO2 permeability. And also in this image, you can see that PET applications when fiber applications is excluded. And 97% of the PET product is used in the packaging sector when fiber applications excluded. And PET bottle accounts for 67% of the market share in the beverage industry. So why we need to recycle it? In 2020, production of plastics reached more than 400 million metric tons. And globally, PET accounted for 12% of the total solid waste. And this shows us that importance of the PET recycling. And the driving force of the PET recycling is it's widely used, and also it is not deteriorate under normal conditions. So in here we can see the methods, and in here PET can be recycled by using mechanical recycling and chemical recycling methods. And mechanical recycling causes degradation of the PET properties, which leads to formation of low quality products. And this drawback not encountered when we use chemical recycling methods. So, and also chemical recycling methods divided to other methods, which are called as methanolysis, glycolysis, hydrolysis, and other processes, which are ammonolysis and ammonolysis. And also hydrolysis divided to 3 subgroups, and these are acid, alkaline, and natural. So our aim in this study is determine the most efficient, most appropriate, and easiest chemical method and catalyst for the recycling of PET to obtain BHET crystals similar to commercial ones. And BHET is the monomer of the PET. So this diagram shows us the method that we used. First of all, PET bottles or polyester yarn, ethylene glycol, and catalyst were put into 2 flasks, and the obtained mixture was heated and mixed. After that, distilled water were added to an empty flask, and the solution was filtered through a stainless steel filter mesh into flask containing water. And as a result of this process, fraction 1 is separated. After that process, the mixture again mixed and heated. And after that, the obtained solution was filtered by a vacuum filtration system. And as a result of this process, fraction 2 was separated. And the final filtrate was stored in a refrigerator for 48 hours. And this filtrate contains BHET. As a result of this process, needle-like BHET crystals were collected through a vacuum filtration system, and the obtained BHET crystals were dried by vacuum oven, and this is called as a fraction 3. So our methodology our study divided to as experiment with different input materials and experiment with different catalysts. Experiment with different input materials covers the glycolysis experiment with using zinc acetate and different input materials. And these input materials are transparent PET, polyester yarn with and without finish, and colored PET. Experiments with different catalysts covers using input materials, transparent PET, and catalysts, different catalysts. And these catalysts are zinc acetate and 1,3-dimethylurea zinc acetate deep atactic solvent. So from here you can see the BHET crystals obtained from the different input materials. And the only difference is that the colored PET BHETs are yellowish. So in this slide, you can see that PET conversion rates and BHET yields obtained from the experiment with different input materials. PET conversion rates are higher than 98% regardless of the input material. And also the yields are high. When colored PET was recycled, the BHET yields are lower than the others. And this is due to the removal of colorants and the additives. And in here you can see that FTR spectra of the BHETs obtained from different input materials. And on the table shows us which groups the absorption peaks in the FTR spectrum of commercial BHET correspond to. And the FTR spectra of the obtained BHETs also showed similar peaks with the commercial one. In here you can see that DSC and TJ thermograms of the BHETs obtained from the different input materials. And a sharp endothermic peak at 110 degrees Celsius can be shown thermograms of the both obtained BHETs and the commercial BHET. And in the TJ thermograms of the obtained BHET has similar decomposition profile with the the commercial BHET. In here you can see the BHET crystals obtained from using different catalysts. And in here you can see PET conversion rates and BHET yields obtained from the experiment with different catalysts. The PET conversion rates higher than 99%, and the BHET yields higher than 75%, regardless of the used catalyst. And also we can see that FTR spectra of BHET is obtained from the experiment with different catalysts. You can see that FTR peaks of the obtained BHETs are same with the commercial one. And also we don't see the catalyst peaks in this obtained BHETs FTIR spectra. And in here we can see the DSC and TJ thermograms of the BHETs obtained from the experiment with different catalysts. And in DSC thermogram, we can see that a sharp endothermic peak at 110 Celsius in both thermograms of the commercial BHETs and obtained BHETs. And also in the TJ thermogram, obtained BHETs have a similar decomposition profile with the commercial one. So as a conclusion in the study, PET glycolysis reactions were carried out using transparent PET bottles, green bottles, polyester with and without finish, as the input materials, and the zinc acetate and 1,3-dimethylurea zinc acetate dielectric solvent as the catalyst. The chemical structure and the thermal properties of BHETs were not very much affected by the input material and the catalyst. Also, the use of the zinc acetate as a catalyst was observed to be more efficient in terms of BHET yield. So as the future work, our future work is to perform an NMR to evaluate purity of the obtained BHETs, to conduct recycling of other input materials, to conduct glycolysis experiment by using other catalysts, and to produce new materials from monomers yielded from conducted chemical recycling of PET. So these are my references, and thank you for listening me.
For this presentation. Is there any question? Herhalde değil mi? Peki. Teşekkür ederim. Sağ olun. Bugün en son sanayi sunumumuz. Teşekkür ederiz. İSKUR'dan olacak.
Geçen sene 40.
Ama giriş yapıyorsun şu animasyonu açabilir misin? Hemen giriş yap. Önce gidiyorum önce sonu açalım. Ben şimdi geri geliriz. Ondan sonra videoya geçeceğim. Geldi mi? Tamam. Ömer hocam ses geliyor mu?
Geliyor hocam. Benim geliyor mu?
Şimdi videomuzu, gerçi sende de vardır video da. Ben başlatıyorum. Ses gelecek mi sana? Bir dakika.
Ses gelmiyor şu an.
Gelmiyor mu?
Hayır. İsterseniz ben oynatayım burada.
O da olabilir.
Tamam, ben oynatayım. Ben oynayayım.
O zaman şöyle yapalım. Sen oynatıyorsan. Paylaşımı durdurdum ben. Sen de. O 5 dakikalık video var mı sende?
Hayır.
6,5 dakikalık video var. Var mı sende?
Yok, hayır. Tamam, siz oynatın.
Tamam, ben oynatacağım. Bekle biraz. Ses geliyor mu? Video ile birlikte.
Geliyor hocam.
Üretiyoruz, tasarlıyoruz, giydiriyoruz. Ya sonra? Tüketim, israf, atıklar, çöp dağları. Tekstil tüketimi dünyanın karşı karşıya kaldığı sorunlar listesinin ilk sıralarında. Zorlu üretim yolculuğu bilinmiyor. Tüketiliyor, tüketiliyor, tüketiliyor. Giysilerin kullandıkça var olduğunu, işimiz bitince dünyadan silindiğini sanıyoruz. Oysa çöpe giden yok olmuyor. Dünyanın yükü durmadan artıyor. Üretimde ve tüketimde israf, iklim ve çevrenin katli anlamına geliyor. Çöpe atılan kullanılmış giysi hacmi yıllık 15 milyon tonu aşmış durumda. %10'u üretim aşamasında çöpe gidiyor. Moda endüstrisi, dünya devi. En çok üretip en çok zarar vereni. Sadece bir tişört için 2,5 metreküp su harcanıyor. Bir kamyon giysi binlerce metreküp su demek. 1 kilogram tekstil için 2 kilogram karbondioksit havaya salınıyor. Tahmin edilemeyecek kimyasal malzeme, boya ve boşa giden enerji cabası. Böyle devam edersek daha çok giysi, daha az yaşanabilir bir dünya anlamına geliyor. Kaybettiğimizi geri kazanmak için yol belli. İskur'da israf etmiyoruz. Yeniden üretiyoruz. Pamuğa, ipliğe, kumaşa sahip çıkıyoruz. Pamuk kıymetlimiz. Hikayemiz çok geçmişe, Kahramanmaraş'ın verimli topraklarına dayanıyor. Elmas gibi koruyoruz. Peki nasıl? Sürdürülebilir tekstili nasıl başardık? İklim değişikliği tekstil için stratejik bir konu. Aksi halde sürdürülebilir bir yol vaat etmiyor. Türkiye'de hazır giyim pazarı 120 milyar liralık büyüklüğe ulaştı. Bu hacmin sürdürülebilirlik oranı sadece %5. İskur'da sürdürülebilirlik tanımımız ise net. Gelecek nesillere ekolojik, ekonomik ve sosyal koşulları devam ettirilebilir bir dünya bırakmak. İklim risklerini tanımladık. Karbon salımını azalttık. Rüzgar, güneş, hidroelektrik enerjisi kullanıyoruz. Recycle üretimi için geri dönüştüremediğimiz atıkları BES santralimizde buhar ve enerjiye dönüştürüyoruz. Su kullanımını azalttık. Atık suyu da arıtıyoruz. Her gün tonlarca kiloyu bulan harman atığı israfını durdurduk. Pamuk ipliği tozlarının hava kirliliğine etkisini yok ettik. Boyamada zararlı kimyasal kullanmıyor, ekolojik çevre yönetim sisteminde ideali gerçekleştiriyoruz. Geri dönüşüm pamuk elyafı içeren iplik ve kumaş üretiyoruz. %100 temiz enerji kullanan İskur'da üretim kapasitesinin yarısı recycle. Organik, CMIA, BCI, hemp, Ecovero, Refibra gibi sürdürülebilir elyaflardan oluşuyor. Geleceği koruyarak ve geri dönüştürerek değiştiriyoruz. Dünya çapında tekstil ürünlerinin %95'i giyilebilir olmasına rağmen sadece %20'si geri dönüştürülüyor. İSKUR'un ana hedefi ise %100'ü sürdürülebilir bir tekstil sektörü. Daha iyi bir dünya mirası için geri dönüşümün geleceğini yazıyoruz. Türkiye'nin tekstil ve ham madde ihracatı yapan en büyük üreticilerinden İSKUR'un geri dönüşüm stratejisinde amaç, kullanılan malzemeleri toplamak, ayırmak, yeniden işlemek ve yeni bir ürün elde etmek. Kumaşlar toplanıyor, aşama aşama elyafa dönüştürülüyor. Varış noktası iplik tesisleri. İSKUR günlük 250 ton iplik üretim kapasitesine sahip. İpliğin %25'i tekstil atıklarının geri dönüşümüyle elde ediliyor. Türkiye'de geri dönüşüm alanında uluslararası Inditex onaylı, OECO-TEX ve GRS belgeli post-consumer ve pre-consumer üretim yapılıyor. Geri dönüşüm ürünlerinden elde edilen elyaflar, Türkiye Cumhuriyeti Sanayi ve Teknoloji Bakanlığı tarafından onaylı Ar-Ge merkezlerinde kontrol ediliyor, İSKUR iplik işletmelerinde çok fonksiyonlu ipliklere dönüşüyor. Geri dönüştürülmüş tonlarca elyaf, recycle olarak kullanılıyor ya da daha fonksiyonel iplik üretimi için harmanlanıyor. Recycle üretimin yapıldığı İSKUR işletmelerinde toplam alanı 400 bin metrekareyi aşan tesislerde her gün en az 50 ton iplik dönüştürülüyor. Her gün 110 bin tişört, 100 bin jean pantolon üretebilecek kadar atık tekstil ürünü geri dönüşüm tesislerinde yeniden hayat buluyor. İpliğe, pamuğa, kumaşa yeniden hayat veriyoruz. Dünya az yoruluyor, kaynaklar çok korunuyor. Hedef, tüm üretimin sürdürülebilir ham maddeyle gerçekleşmesi. Sürdürülebilir iplikle kaynaklara sahip çıkıyor, sürdürülebilir kumaşla ekolojiyi esas alıyor, sürdürülebilir tekstille geleceği koruyoruz. Sürdürülebilirlik hepimizin sorumluluğu. İSKUR, geleceği dönüştürüyoruz.
Evet arkadaşlar, ben de Levent Hocam'a teşekkür ediyorum. Levent Hocam teşekkür ederim hocam. Bir sonraki ortak oturuma hemen